Hey everybody, we are going to study analyzing graphs of polynomial functions today. And the first things we're going to do is first we're going to compare zeros, factors, solutions, and intercepts and compare how they go together. So let's just say that we had some f of x in this form. Now keep in mind, this form of f of x is just it could be any polynomial function where this value of n is the degree, it's its highest degree, and it descends in degrees or in powers down. So here's the thing. We've been talking a lot about zeros and talking a lot about factors and solutions, and we want to compare how they are similar and different. So here is what a zero is. A zero is the value of k, which is a solution or an x-intercept of the polynomial of function f. So k is a zero of f of x. Okay. A factor, the factor x minus k is a factor of f of x. A solution is the value of k is a solution, meaning it solves the polynomial equation f of x when it's set equal to 0. And lastly, an x-intercept, I should say, is k when k is a real number and k is an x-intercept of the graph of f of x. And f of x passes through the point k comma 0. So notice here, and I wasn't getting lazy and picking my values, this value of k, whatever is a 0, was the same value of k that is a factor, is the same value of k that is a solution, and is the same value of k that's the x-intercept. And that's because they literally are all the same value, they're intertwined, and this is what we're looking for. So for example, let's use the x-intercepts to graph a polynomial function. Okay, so number one, when we've got a function that looks like this, notice how here we've got parentheses. Okay, we can call this, it's in factored form, or we could use this factored form to find the x-intercepts, aka the zeros. And in order to plot the intercepts, we would set each parentheses equal to 0. So I see two different parentheses here. I see one here at x plus 3, and I see another parentheses here at x minus 2, but see this 2 right here? That 2 tells me that there's a multiplicity, which means it hits it more than once. So again, we're going to go back. We're going to set each parentheses equal to 0. And now we're going to solve. So if x plus 3 equals 0, that means x equals negative 3. And if x minus 2 is 0, that means x equals 2. And then as I'm going to add that information to my graph, and actually I'm going to use my graph paper. Okay. Let's just say here's my graph. All right. Okay, so we're going to start adding our information that we're finding to our graph. Here's our x-axis, here's our y-axis. And remember, our intercepts, meaning our x-intercepts, are at x equals negative 3. So here's negative 1, negative 2, negative 3 is an x-intercept, and so is 2. Okay, so those are my x-intercepts. And then step 2 is I'm going to plot between and beyond those x-intercepts. So here's what that means. I'm going to find some values of x and find the corresponding values of y, but I'm going to pick them so that they're to the left and the right of each x-intercept. Okay, so if I've got x equals negative 3 as an x-intercept, I'm going to pick values like negative 4 to the left of it. To the right of it, I could pick a 1, a 0, to the left of 2, I could pick something in there like the value of 1. And to the right of 2, anywhere on the right, I could pick a value of 3. I just pick the ones that are easiest to work with. And then I'm just going to plug them in to that function that we were working with before. So for first one, I like to do the easy one first. I'm going to pick 0. So I know 1/6 times 0 plus 3 times 0 minus 2 squared is like saying 1/6 times 3 times negative 2 squared, which is 1/6 of 3 times positive 4, which is 1/6 of 12, which is just 2. Okay, so I'm going to do that work on each of these. I'm just plugging them in. And if we plug them in on each of these, I'm going to get, this is a value of 3, this is a value of 2/3, this is a value of 1. And if I plug in negative 4, I'm going to get negative 6. So I'm just going to graph those and plot them on my graph here. So we're going to go negative 4, negative 6. So 1, 2, 3, 4, 5, 6, comma negative 4, 1, comma 3, 0, comma 2, 1, comma 2/3, and 3, comma 1. Okay, so those are some of my graphs, or excuse me, some of the points that we just plotted. We're good on that. And then my third step is I'm going to determine the end behavior. So remember, end behavior, remember that chart that I showed you last section where we have plus and positive and negative leading coefficients and even and odd degrees. So remember, if it's positive, it always ends up. If it's even, they match. If they're odd, they go opposite. Similarly, if it's negative, it's going to end down. If they're even, they match. And if they're odd, they go opposite. So we're going to use that little chart that we learned before and evaluate our end behaviors. Remember, we're going to go back to our function. Now, this is where it gets a little bit tricky, is that this is in factored form. So if I were to multiply this out, remember, I'm only looking for that leading term, that leading coefficient. So I'm just going to multiply the first part of each of these. So 1/6 times x squared is going to give me my leading coefficient. So we say 1/6 times x squared, and that gives me 1/6 x to the third. So that's going to tell me that we're looking at our chart here at a positive odd. So this is positive odd, that's this graph right here. So we're ending to the right, going up. So I'm going to take my last value to the right here, and from there I'm going to go up with it. And I'm going to take my last value to the left, and I'm going to go down with it. Okay, so that was my end behavior. And then my step 4 is I'm going to kind of connect these dots and draw these curves. So I'm just going to connect the dots that I have and make it a nice smooth curve. And that is an approximate shape of the polynomial that they gave us. So again, to graph the polynomial that they gave us is number 1, you plot the intercepts. So we're going to find the x-intercepts by setting each factor to 0. Put those on the x-axis. Then you're going to plot your points in between and beyond each of those intercepts. So I picked values to the left and the right of every solution or 0. Determine your end behavior, which told us that this was going up to the right and down to the left. And then we drew the in-betweens. Okay, now let's talk about turning points. So this right here is a function of f of x. Okay, it's some function. We can see here there's a couple of different turns. It changes direction. So here's the thing. We see 2 of these turning points right here. One, I could call this like a mountaintop, right? Like if I were to hike it and say, oh, I'm on the top of the mountain, we call that a local maximum. And what a local maximum is that it's the highest point. It's higher than all of its nearby points. So like if I were just to zoom in that region and not see what else is going on, I can see this is the highest point. So if I was standing there, I'd say, oh, hi, I can see the view. It's because it's the highest point, so we know that's a local maximum, okay? And if we were looking for a local minimum, I would kind of look for something that looks like a valley, like this. So if I were just kind of zoom in right there, I don't know what's going on anywhere else, but I know in this region for the graph, this is the lowest point, or like a valley. So that's going to be our local minimum, which is lower than all nearby points. Okay, so here's what we know about that. Okay, so we're going to see peaks and valleys, aka local maximums and minimums, on every single polynomial. And here's how to know how many we can expect there to be. Okay, there are turning points, aka local maximums and minimums, and we can think about two different ways. The graph has at most n-1 turning points, or peaks and valleys, as if the degree is n. So if n is the degree, we know at most there can be one less than the degree, peaks and valleys. Also, if there are distinct real zeros and f of x has n distinct real zeros, then it has exactly n-1 turning points. So if we look at the zeros, so like for example, this one works for both. Okay, so I see here for the first part right here, it says the graph is at most n-1 degree turning point. So I could say I know that the degree of this f of x is x to the third. Notice how there's only two of these turning points. And that's because if n is 3, one less than it is 2. So whatever your degree is, you have at most that many turning points. The other thing that we want to look at is, and I'll put this in purple, is that if it has n distinct real roots. So here's the thing, a real root is just where it crosses the x-axis. So we see 1, 2, 3 real roots here. If there's 3 real roots, it said that there would be one less turning points. So look at that, there was 3 real roots, and look, there was only 2 turning points. So both of those are true. So now we're going to use our graphing calculator to identify the x-intercepts and points where local maximums and minimums occur. Okay, so if you're going to use your graphing calculator, you could also use Desmos, which when we put it in there, I'm going to show you what it looks like. We're going to go ahead and put Desmos in here, and what I would do is go over here, go to desmos.com, and you're going to type in the function that you want to graph. So this is going to be x to the third, so this is the exponent key right there, minus 3x squared plus 6. Okay, so what we're looking at here is it's this graph, it's got these turning points here, and I'm going to go ahead and just snap a little screenshot of that, and I'm going to add it to our notes so you can see what I'm talking about. Okay, and I'm going to change our paper so you can see. Okay, so looking at this graph here, I can see the shape of my graph, which I used a graphing calculator on. So now we're going to identify the x-intercepts. And the points where a local maximum and a local minimum occur. So let's first do our x-intercepts. Remember, x-intercepts is where the function crosses the x-axis. And we know for this, here's my x-axis. So I only see it cross one time, and it's approximately at, if this is -2, here is -1. So this is like at x equals -1.25 approximately. So our x-intercepts are at x equals -1.25, and to write that as a point, we go -1.25 comma 0. Okay, remember our local max is like a peak or a top of a mountain, so we see that right here. We see that as a local max. And the way that we would say that is, first we're going to look to see, okay, what is our height at that local max? We saw that it was at 6. So whenever we talk about a maximum or minimum, we're talking about the y value, which in this case is 6. And then we would say, actually, instead of at, we say of, pardon me. We have a local max of 6 at, and then we say the location where x is, x at 0. So when x is 0, y is 6 at the maximum, and that is how we write it. So let's look at our local minimum now. Remember, a local minimum is like a valley. So here's our point of our valley. And we see that our value of y is 2. So our local minimum of 2 is at when x equals 2. And that's how we would write it as well. Okay, that's it for our notes for today, and I'll see you in class.